Hello everyone. In this presentation, I would like to introduce our recent work, Fluid Dynamic DNNs for Reliable and Adaptive Distributed Inference on Edge Devices. My name is Lei Xun, and this work was in collaboration with Mingyu Hu, Henry Zhao, Professor Amit Singh, Professor Jonathan Hare, and Professor Jeff Merritt. First, let me give you some background. DNN inference is increasingly being executed on local devices thanks to its low latency and improved privacy. However, these models are both computationally and memory access intensive. Many efficient inference techniques, such as pruning, quantization, and distributed inference, have been proposed in the past. In this research, we focus on distributed inference. Previous distributed inference, mainly focusing on how to split a static computation graph, typically based on the computing capability of each networked device. Here, for example, we have a static DNN model, and we have two devices, one master, one worker. Assuming these two devices have the same computing capability. Now, if we want to distribute this static model onto these two devices, we can split the model into two equal portions and deploy them onto the two devices. This is the case when no device failure happens. However, at the system runtime, the device could fail. Master device could fail, worker device could also fail. Because we are running a static DNN model on these devices, during the inference of a static DNN model, all the model weight must be used. Otherwise, we get a random result. Here, we basically have half of the model weight on one device, half of the model device on another device. So if the master device fail, the worker device will fail. And if the worker device fail, the master device will fail as well, because these remaining online devices only have a part of the model weight, and they cannot be used for inference. And the question we try to answer in this research is, can we co-design a model to solve this problem? The answer is yes. Dynamic neural networks is an emerging research field for model design. So the key idea about dynamic neural networks is to use specialized training algorithm to support the partial execution of the full network. Here I have an example from previous work. The full networks is divided into three portions. The model is trained incrementally, one portion at a time. So at the step one of incremental training, only portion A is trained. In step two, only portion B is trained while using the pre-trained weight from A. And in the final step, only portion C is trained while using the pre-trained weight from A and B. So here, what we have is not three separate models. What we have is a one full network with two sub-networks. So A and AB, they are both sub-networks of the full networks. They share the weight together. And typically, smaller sub-networks has lower accuracy, but also lower latency and energy and power consumption. So comparing the dynamic model with the static model, you can consider the static model as the full network, and we retrain the static model using specialized training algorithms such as incremental training, so that we enable the partial execution of the static model. So for a static model, let's say if we took only A, which is 25% of the weight, out directly to do the inference, we get a random result and a very low accuracy. But because we retrain the model using incremental training, now if we took a 25% model from the dynamic neural network, we actually have a lower accuracy, but it's also a reasonable accuracy. It's no longer random. It has a clear trade-off between accuracy, latency, and energy power consumption. Now, if we look at the device failure again, so when the master device fails, the worker device will also fail, because these dynamic models are trained incrementally, meaning bigger model, the bigger subnetworks or full networks always rely on the bottom weight, the smaller subnetworks. Now, because the bottom 50% of the model weight are deployed on the master device, and the upper 50% of the model weight, which is the model weight between 50 and 100%, are deployed on the worker devices. Now, if the bottom 50% of the model weight is missing, the upper 50% of the model weight can no longer be used for inference. We will get a random result by doing inference using them. However, on the other hand, if the worker device fails, because the master device holds the bottom 50% of the model weight, these are supported subnetworks from the dynamic DNN configurations, so that we can actually run the 50% model or even 25% model for inference at reduced accuracy, but also reduced latency and energy power consumption. So the question is that, can we design a better model so that when the master device fails, the worker device can also run the inference independently? So this leads to the design of this work, fluid dynamic neural networks. So the idea behind the fluid dynamic DNN model is to train a static model using a novel nested incremental training algorithm. I will talk about it in the next slide. So basically what this algorithm doing is to reduce the dependencies between subnetworks. In other words, reduce the dependencies between the bottom 50% of the model weight and the upper 50% of the model weight. So in a standard dynamic model, if we took the upper 50% of the model weight, such as C or CD out, and use them for inference, we get random result because these model weights are not trained to do inference independently. Now, in the fluid dynamic DNN model, we use nested incremental training to support the another basically 50% model using only the upper weight, upper 25% and upper 50% of the model weight. So here's a summary of the model configurations for static DNN models, because all the weights must be used. So the configuration is ABCD. For dynamic DNNs, it also has the full network ABCD, but it also has in this case, in a full incremental model design, it also has three subnetworks. In the case of fluid dynamic DNN models, because we decouple the dependencies between subnetworks, now we have two additional subnetworks, another 25 and a 50% model using the upper model weight. Now let's have a look at the model failure scenarios. So for static DNN model, as I mentioned here, all the model weight must be used for inference. So any one device failure could cause system failure. For dynamic DNN models, when the worker device failure, the master device can run a smaller, basically bottom 50% of the model weight or bottom 25% of the model weight to do inference. However, when the master device fail in the dynamic DNN models, the upper 50% of the model weight cannot be used for inference, hence cause another failure here. Now, this is the problem we try to solve using the fluid dynamic DNN model and a nested incremental training algorithm. So in fluid dynamic DNN model, because the master device holds the bottom 50% of the model weight, the another device hold the upper 50% of the model weight. So any one device failure will not cause the system failure because they can all running the inference independently. Now let's have a look at the nested incremental training algorithm. So here is the algorithm. At the beginning, we need to build a foundation for this training. we first train a dynamic neural networks, a standard dynamic neural networks. We first train the 25% model, then we copy the weight, pre-trained weight, to the 50% model. In this step, we basically train B using the pre-trained weight from A. And so on and so forth, we get the standard dynamic DNN model with one full network and three subnetworks. Now, if we copy the weight from C and CD directly for inference, we get the random result because they are not trained to do so. So the core of nested incremental training is to copy the upper 25% weight, and we retrain this part, and we retrain the part and treat this part as a individual new 25% model. And then we copy this pre-trained 25% model to the upper 50% of upper 50% model. We train this model, and finally we copy the retrained upper 50% of the model weight back to the 100% model. And we do this process in multiple iterations so that the final model is tuned to support the decouple between the lower 50% of the model weight and the upper 50% of the model weight. We tested this idea using a small DNN model with 3 convolution layers and 1 fully connected layer. It has 4 subnetworks. We tested the accuracy on MNest dataset, and we tested the throughput on the CPU of a NVIDIA Justin platform. So here's the accuracy and the throughput result. First, you can see that static DNN fail when any device fails. So here we can only report the model accuracy and model throughput when both master and worker devices are online. For dynamic DNN model, it can still work when the worker device fails. In another word, we can run the 50% model on the master device. And because the model is this subnetwork model is smaller than the full network, we run the inference at a reduced accuracy. And also here, because the worker device failed, there's no communication needed between the master and the worker device, hence reduced communication overhead and boosted the throughput a little bit. For fluid dynamic DNN model, because the master device holds the bottom 50% of the model weight and the worker device holds the upper 50% of the model weight, they can all run in the inference independently. So in this case, when any one device fails, the other device can still run the inference. But of course, because they hold the 50% of the model weight, they will be running at reduced accuracy, as well as due to the remove of communication overhead, the throughput is boosted a little bit. In the case of when both devices are online, we can also use the fluid dynamic DNN model in 2 modes. One is the high accuracy mode. As you can see here, we allow the communication between 2 devices to form the full network. You can see the high accuracy mode has the highest accuracy. Or we can run the model into a high throughput mode. Basically, we cut any communication between 2 devices and let them run as basically 2 independent inference devices. Now, in this case, we boosted the throughput a lot. So basically, dynamic DNN model bring additional trade-off opportunities compared to the static model. And the fluid dynamic DNN model bring even more trade-off opportunities into the space. This is the end of my presentation. You can find more about our previous works on dynamic neural networks here, and you can also see that we are presenting 2 works at date 2024. You are welcome to our poster and have a discussion with us if you have any questions. Thank you and have a good day.